A flash green campus, affiliated to JNU Hyderabad and approved by AICTE, accredited by NAC with B++ grade.
State-of-the-art infrastructure. Highly experienced and well-qualified staff members. Offers civil, electrical, electronics, mechanical and computer science engineering undergraduate courses.
Separate boys and girls hostels with all the facilities. Entire campus is Wi-Fi connected. NCC and NSS wings as co-curricular activities.
90% of eligible students get placed in various companies every year.
I am Dhanlakshmi, TCS.
I am Sindhu, working with Wipro.
I am Anukya, Infosys.
My name is Naredi Shivangi Agrawal, presently cognizant company.
I am Anurag Suram, Wipro.
I am placed in TCS.
I got placed in Unschool, which is an edutech company. I've got placed in ILM.
I got placed in Tata Groups.
I have placed in two companies, Q Spiders and J Spiders and Topper.
I have selected in Topper company.
I am placed in DXC Solutions.
I got placed in TCS.
I was placed in ILM and Topper.
Major recruiters are Infosys, Wipro, Cognizant, HCL and many more.
Okay, starting.
What happens when you die? You become a ghost.
These people were declared.
Noted as Kids Singapore, established in 1997 by Orthala Education Society, located in the midway of Karimnagar and Warangal Highway.
Spread over 30 acres
I
of
request,
lush green
good
campus,
morning to all.
affiliated to
I
JNU
request all the
Hyderabad and approved
parents,
by
please
AICTE,
mute your
accredited by NAC
videos
with
and
B++
mic.
grade.
State-of-the-art infrastructure. Highly experienced and well-qualified staff members. Offers civil, electrical, electronics, mechanical and computer science engineering undergraduate courses.
Separate boys and girls hostels with all the facilities. Entire campus is Wi-Fi connected. NCC and NSS wings as co-curricular activities.
90% of eligible students get placed in various companies every year.
Good morning to all. This is Dr. G. Mallaya, working as a professor in the Department of Mechanical Engineering and coordinator of today's webinar. First of all, I would like to thank our management and principal sir for permitting us to conduct one-day webinar on 15th June, that is today. It is my great pleasure and honor to welcome you all for the one-day webinar on advances in manufacturing processes and optimization algorithms, organized by the Department of Mechanical Engineering, KIT Singapore, Hyderabad. Today webinar is focusing on the advances in manufacturing processes and optimization algorithm. The primary goal of this webinar is to promote research activities in mechanical engineering, especially in the area of manufacturing, like additive manufacturing and surface modification techniques like frictional stage processing, etc. And also in optimization techniques or algorithms. I would like to take this opportunity to express our sincere thanks to today's speakers, Dr. A. Kumar, Professor, Mechanical Engineering Department, NIT Warangal. And second speaker is our HOD, Dr. L.V. Satish Kumar sir, for readily accepting our request and sparing their valuable time for presenting their lectures and sharing their knowledge. I also thank all the participants for attending this webinar, and I hope you will gain some information and knowledge in the areas of your research. I wish this webinar is successful and reaches its goal. All the best. Thank you, sir, for giving this opportunity. Now, I would like to invite our beloved principal, Dr. K. Shankar Garu, to share his views about this today's webinar. Sir, principal, sir.
Good morning to all of you. Respected Professor A. Kumar from NIT Warangal, our head of the department, Dr. M.B. Satish, coordinator, Dr. Mallaya, other friends from different institutions. First of all, I appreciate the mechanical department for organizing this one-day webinar on advances in manufacturing process and optimization algorithms. I take this opportunity to convey my sincere thanks to Professor A. Kumar for accepting our invitation to deliver a keynote lecture today on this topic. And also I convey my sincere thanks to our head of the department. He is also giving lecture on optimization algorithms. On this occasion, I would like to give a brief introduction about this institution. Kamala Institute of Technology and Science, established in the year 1997 by Oditala Education Society. Captain B. Lakshmi Kantarao Garu is chairman of this institution, and Sri V. Satish Kumar, MLA from Husnabad constituency, the secretary and correspondent of the institution. Now, at present, we are offering 5 undergraduate courses with an intake of 540 and 1 PG MTech course in mechanical engineering, advanced manufacturing system by our mechanical department. And this institution is also accredited by NAC B++ grade and also accredited by TCS Hyderabad for placement purpose. I once again convey my sincere thanks to Professor A. Kumar Garu for accepting the invitation, and also I convey my sincere thanks to all the participants for sparing your valuable time with us. Thank you one and all for this opportunity given to me. Thank you.
Sir, thank you, sir. Thank you, sir. Thank you, sir, for your sharing your views about this today's webinar. Thank you, sir. Now, I would like to invite our beloved HOD, Dr. M.B. Satish Kumar sir, to share his views about today's webinar. HOD, sir.
Good morning, everyone. Good morning, everyone. Our beloved principal, Professor K. Shankar Garu, coordinators of this program, Dr. G. Mallaya Garu, and Mr. Amarnath, participants both external and internal, a very good morning to you all, and special good morning to our guest speaker today, to Dr. A. Kumar Garu. So in the name of COVID, we got this opportunity to organize a online webinar on this topic, advances in manufacturing processes and optimization algorithms. So I feel very happy and also congratulate the coordinators for taking initiative in organizing this program. And in the name of this webinar, we got an opportunity to be in contact with persons from various parts of the country. I hope the lectures you will enjoy and you will get some information and knowledge through these lectures. I wish you all good day. And now I request our Professor Dr. Mallaya Garu to introduce the first speaker, Dr. Kumar Garu. Thank you, everyone.
So, thank you, sir, for your valuable words. Now I would like to introduce today's first speaker, Dr. A. Kumar sir. Dr. A. Kumar sir is presently working as professor in the Department of Mechanical Engineering, NIT Warangal, Telangana State. He has completed his diploma in Mechanical Engineering from Government Polytechnic Warangal District in the year 1991. He did his BTech in Mechanical Engineering from Kakatiya Institute of Technology and Science, that is KITS Warangal, in the year 1995. He did his MTech in Production Engineering specialization from SV University, Tirupati, Andhra Pradesh. He also did his PhD from Usmania University in the year 2008 under the guidance of Dr. S. Sundararajan sir, former director BrahMos, DRDL Hyderabad in the area of simulation and characterization of aluminum alloy elements. He has more than 20 years of teaching experience and 12 years of research experience. His research areas are additive manufacturing, friction stir welding processing, modeling of friction stir welding processes, fabrication of composites by casting processes, and electrical discharge machining of titanium and superalloy. He has guided 8 PhDs and 6 are under progress. To his credit, Sir has published 55 papers in highly reputed international journals. He has completed 4 projects worth of rupees 47 lakhs at the Mechanical Engineering Department of NIT Warangal. He has filed 2 patents. First patent is filed on system and method for reinforcing powder particles using friction stir processing. Second patent is filed on abrasive ceramic bonded tool for friction stir welding. Sir is reviewer for various journals like Materials and Design, International Journal of Advanced Manufacturing Technology, Material Science Engineering, a Journal of Materials Research and Technology, and Indian Journal of Engineering and Material Science. He is the Fellow of Institution of Engineers, India, and also life member of various bodies like MISTE, MIWS, MSQAR, and MIIW. He is awarded with the IIM SAIL Gold Medal 2018 award as one of the co-authors of the technical paper on influence of welding techniques on heat-affected zone softening of dissimilar metals, marrying steel and high-strength low-alloy steel, gas tungsten arc weldments. Published in the Transactions of the Indian Institute of Metals during the year 2017 and 18 in Ferrous Group. He is also BOS member of various institutions, more than 4 institutions. He is also a member in various committees. Sir is also conducted short-term courses, more than 7 short-term courses and workshops. And to his credit, Sir is writing a chapter in the prestigious journal Springer entitled Application of Mura Method for Friction stir welding Tool Material Selection. So, kindly apologize, sir, for reading the brief profile of yours. So now I request. See, I am very happy to inform you that all the participants, Satish is my PhD guide in my research. He has encouraged me and helped me in my research in the area of welding of steel. So I thank you, Dr. A. Kumar sir, for helping me in my research and guiding me for awarding the PhD degree. So now I would like to invite Dr. Kumar sir to start his presentation. Thank you, sir.
Okay, thank you very much for introducing me to the audience, Dr. Mallaya, and respected the principal of the KITS Hyderabad and HOD of Mechanical Engineering Department and conveners of this one-day program. First of all, I congratulate to the KITS management and as well as the department and the coordinators of this program. So they have chosen the right topic, that is advanced in manufacturing process and optimization algorithms. So we can use algorithms everywhere and in manufacturing process as well to optimize the certain parameters to get the final components. And also I'll thank to the Mallaya as well as other members of the programming committee to give me this opportunity to share my knowledge in front of you. And welcome to the FDP program for all the participants, and I can start my presentation. Okay. Are you able to see the screen? Malaya?
Yes, sir. Yes, sir.
Okay. And I am audible?
Yes, sir. Now it is clear, sir. Now it is clear, sir.
Okay. So today's topic is advance in manufacturing process. I'm going to touch upon the latest technology which are used in development of product for various manufacturing techniques. So especially we are working on the related fields like wire arc additive manufacturing and friction stir additive manufacturing, 3D printing, and with that we can give some extra knowledge to you to go for further research. That's why I fixed some of the topics. So I think most of the participants may be aware of the friction stir welding and submerged arc welding and MIG welding and TIG welding, etc. So with the use of those techniques, we can do some extra additional features added to that. Then we can develop the new product or new process. So that is useful for development of our products. Basically, any manufacturing process comes under any one of the areas, or we can say if you want to develop any product, either you can use any one of the technique or combination of the techniques to produce your components. Suppose I want to develop a product of this nature, then I want to remove the material from the stock. Finally, I am going to get the new product that is known as a subtractive process. So you have to remove the material from the stock, then finally you are going to get the component that is useful for the direct applications. So you are removing the material, that's why it is subtractive or negative process, we can call it as. Then coming to next process, additive process, we are adding the material layer by layer onto the substrate so that you can get the final component. So adding the layer by layer, you are adding something to the previous layer. That's why it is additive process or positive process. And the next process, formative process. In this process also, you can also get the final component, but there is no addition or there is no deletion of material from the stock. Only you have to change the geometry from initial to the final one by pressing the material into the die so that you can get the final shape. Then coming to hybrid manufacturing, so nowadays this is a buzzword in manufacturing area. It is not a new process. It is an old process, but we need to combine these two processes into one single machine. Then we can call it as hybrid manufacturing or hybrid process, so that you can save a lot of time to produce the component. That is the idea. So in this additive manufacturing is one area, and other area is subtractive manufacturing, that is machining. Then if you combine these two into a single machine, then we can call it as a hybrid manufacturing process. Suppose if you look at this picture, this is final component you are going to generate through hybrid manufacturing. For that, you need to develop a component through additive manufacturing with the same design. Then you need to remove the material from the unwanted material from the geometry which was developed through additive manufacturing by machining process, and also you can do some finishing process. Then finally you are going to get the final component. So this is small video, just so this is direct energy deposition technique. You are in that you are developing the material by melting the powder particles with the laser, and you can develop the component. Now this additive manufacturing is over. Now you want to do machining.
Now we can add a tool to the holder so that the machining is performed on the component which is produced by additive manufacturing process. Yeah, this is the final component, and okay. So in that, my area is wire arc additive manufacturing process. There are some other techniques which are going to produce the same component through other technology like stereolithography and powder bed fusion process, direct energy deposition process, so many other 3D printing process we can able to generate the product. But what is the advantage? You are going to see in future slides what is the advantage over to other manufacturing 3D printing process. So wire arc additive manufacturing, the development of wire arc additive manufacturing is being driven by the need for increased manufacturing efficiency for engineering structure. It is able to produce a very near net shape, performs without the need for complex tooling, molds or dies, offer potential for significant cost and lead time reduction, increased material efficiency, improved component performance, and reduction of inventory and logistic cost by local on-demand manufacturing. Without use of any other additional fixtures or tools, you can able to generate 3D components. Whereas in conventional machining process, if you want to generate a 3D object, it needs tools and fixtures, so that it takes a lot of time to complete your job. So it is not a new process. It is patently in 1920. VAM is probably the oldest, outward, simplest, but least talked about the range of additive manufacturing process. Because in those days, the CAD CAM is not developed. So the interface with the CAD CAM and wire arc additive manufacturing machine, then you can able to generate the component very faster way, like the rate of composition of the material 1 to 10 kg per hour, and the layer thickness approximately 1 mm, so that you can able to build the component in a large size. So just you can see the major research groups in wire arc additive manufacturing throughout the world: China, Holland, United Kingdom, France, United States, India, IIT Hyderabad, IIT Tirupati, IIS Bangalore, NIT Warangal, and some other institutions are doing in wire arc additive manufacturing, Australia, Japan, and South Korea. Then if you see the synonyms, the right side of the chart, the welding based deposition, welding based rapid prototyping, 3D welding, 3D micro welding, near net shape manufacturing, hybrid layered manufacturing, shape deposition manufacturing, shape metal deposition, direct energy gas metal arc welding based additive manufacturing, and the multiple plasma arc welding based rapid. So many synonyms like 3D printing. Similarly, we can have so many synonyms related to wire arc additive manufacturing process. So it is a simple principle. It works by melting of metal wire using an electric arc as the heat source. The wire, when melted, is then extruded in the form of beads on the substrates. As the beads stick together, they create a layer of metal. The process is then repeated layer by layer with the robotic arm until the metal part is completed. Using wire as a feedstock, the basic process has been used to perform local repairs on damaged worn component to manufacture round components and pressure well circuits. So it is similar to welding process. Just you can melt the pillar wire and you can deposit the melted pillar wire onto the substrate according to your requirement. That is taken from the STL file from the CAD data. So depending on the nature of the heat source, we can classify into gas metal arc welding based, gas tungsten arc welding based, plasma arc welding based, and also cold metal arc welding based also there. The choice of wire arc additive manufacturing techniques directly influence the process conditions and the production rate for target components.
Kumar sir.
Yeah.
సార్ ఒకసారి స్క్రీన్ షేరింగ్ స్టాప్ చేసి మళ్ళీ స్టార్ట్ చేయండి సార్, కొందరికి కనబడట్లేదు స్లైడ్స్.
Okay. Now it's okay.
No sir, it's not visible. Not visible sir. Once again please try sir.
Okay. From starting onwards it is not visible, huh?
No, sir. Just now, sir. Just now. Miss it, sir. Just now, sir. Yes.
Now?
Oh, sir. Just let us see.
Now it's okay. Now it's okay.
It will visible, sir.
Classification of VAM processes.
No, sir. 1 minute, sir. 1 minute. Not visible, sir. Once again, just stop and start the sharing, sir.
Okay. Oh.
Kumar, sir.
సార్ స్క్రీన్ షేర్ చేసినారా సార్?
స్క్రీన్ షేర్ చేశారా సార్?
ఓకే ఓకే ఇప్పుడు చూడండి.
ప్రాసెసింగ్.
Now it is clear, sir.
Okay.
Please continue, sir. Yeah. Just enlarge it, sir. Enlarge it. F5.
Okay.
Now it is okay, sir.
Okay, sir.
Yeah. The classification GTAW non-consumable electrode, then you can use separate fireweed process, typical deposition rate this much 1 to 2 kg per hour. Now it's okay.
Clear, sir. Clear, sir. Continue, sir. Please continue, sir.
Yeah. Next process, GMAW process. Then nowadays most of the VAM machines are interconnected with the cold metal transfer welding. Because it is a modification of MIG welding process, we have to add the material in cold state, that is below the melting point temperature of the material. That's why we have so many advantages compared to GMAW as a source. Now, the robotic and machine-based system are two types. Robotic-based system includes in capable of manipulation system and CAD/CAM software. And machine tool-based system into which the deposition equipment has been integrated with have additional potential to allow the combination of AM and subtractive cutting process in layer by layer manner, allowing features to create and finish the machine. So this comes under hybrid machining. Here only CAD/CAM is interfacing with the robot. So that robot will take the programming from the CAD/CAM based language, that is STL file. The STL file is converted into robot language. That robot has to move according to the STL file format. Then you can able to deposit the material through melting of the filler wire. So this is the VAM equipment. This is a robot. At the end of the robot arm, MIG welding cold metal transfer gun is attached. Then you can give a programming to the robot. Then accordingly the robot arm has to move. Then you can able to generate the 3D objects. So just you can see the schematic diagram on the other end. Just you are adding the layer by layer. This is a torch. Then you can add the filler wire. Then because of the arc, the filler wire is melted. Then you can give the movement from the robot arm. Then you can also add some inert gas environment to avoid the oxidation during the process. So for the benefit of the participants, I am sharing some of the microstructures of various materials by additive wire arc additive manufacturing process. The first one is titanium 6Al4V and 4043 and inconel 717. Just you can see inconel 717, you can find layer by layer. This is one layer, another layer, another layer. So in between the layers, there is a interface. So that interface is the, we can call it as a metallurgical bond between the two layers. So if metallurgical bond is perfect between the two layers, then whatever the component you are generated through wire arc additive manufacturing or welding or any other process, any 3D printing process, your properties are good. Otherwise, your properties are not up to the mark. Then you should see the compatibility between the two layers by not to form any oxide formation during the process. Then if you look at these various materials, its severity and improve the properties with like porosity, residual stresses, delamination, crack and oxidation, surface finish, deformation. Then if you observe all these things, depending upon the different materials, you can able to succeed in a particular one, not to all others. Then process variables which are included in wire arc additive manufacturing process: wire feed rate, voltage supply, argon flow rate, and weld speed, and number of layers you can add. Then metal transfer in multi-directional GMAW based systems. Just you can see these diagrams. There are two types of mode of metal transfer shown here. One is short circuit metal transfer, other one is spray transfer. In spray transfer, if you melt the material, filler material, the droplets which will force onto the substrate, but it deviates the direction of the position due to the gravity. Whereas if you go for short circuit transfer, there will not be gravity effect is that much. Then you cannot able to deviate from the location of the where material is going to deposit. Yes, you can see due to the gravity, the molten metal is sags from the exact location. So this is unwanted material for the exact applications. So similar, some other structures you can also develop supporting structures by movement of the welding torch in back and forth, so that you can able to generate the components. This is another structure from the bottom to top and the top to bottom. Like that, you can develop the support structures for the main structures. So this is another structures CAD model as well as a real picture I'm showing for your interest. So this is one video in wire arc additive manufacturing. This is one rib and another rib. That's where we started. So this is known as, yes, there are supporting structures. Now here the metal is deposited on the substrate with a certain velocity and certain speed, so that you can able to generate the 3D components very easily. So like that, you can develop the components in through wire arc. So what are the benefits you are going to get? Production of large parts compared to powder bed fusion process as a robotic arm, because the volume of the robotic volume is much higher than the normal 3D printing process. In that case, you can develop the components in very large size and shape compared to 3D printing process. And wire is less expensive compared to metal powders. VAM hardware is less expensive compared to 3D printer. It can deliver near net shape components, minimize the need for surface finishing, good option for repair and maintenance, operation for specific components like turbine blades and also molds and dies. So this is very important for repair applications. We cannot take it out the entire component from that. You can do repair, so that you can go on to the site and you can do repair for the structures, heavy structures. So the limitations of VAM heat management is somewhat difficulty for materials like titanium using inert gas as atmosphere. It limits the size of the parts that can be produced with this technology, and installing such chamber will increase the cost of the equipment. Although a number of companies are developing VAM technology for production, but no commercially available. But as of today, we can combine with KUKA and CMT process, so that we can able to generate the system. For that, you can produce the component in additive manufacturing area. So the applications: aerospace, Stella, and world's first 3D printer, shipbuilding structures. This is the process very much useful. So recently, I have gone through one video. They are producing the ship structures within 1 week using multiple wire arc additive manufacturing process. Not only one single torch, you can also add multiple torches, so that you can increase the build rate for and produce the component and without loss of much time. Now another process is the friction stir additive manufacturing. In the earlier process, we are melting the filler wire, and you can deposit the melted filler wire onto the substrate and allowed to solidify. So some materials not suitable for wire arc additive manufacturing, especially titanium and aluminum alloys. It is very difficult. You have to take a lot of precautions to produce the components through wire arc additive manufacturing. So if you are going to the solid state process, there you are going to generate the components which without much difficulty, because in solid state welding process or solid state process, you are not melting the material. Just you have to heat the material to its recrystallization temperature. So that itself to soften the material, then you can do whatever you want to, you can develop the components. So it is basically originated from the friction stir welding process. In friction stir welding, it is a non-consumable tool is with the shoulder and pin diameter. The tool is rotated with certain RPM, and shoulder has certain features and pin also certain features. The pin is inserted between the materials or in between the layers to be processed. Then the shoulder is always contact with the layer, topmost layer, and rotating shoulder. Due to that, heat is generated. That heat is softens the material, and movement of the material takes from advancing to the retreating side. Then you can able to finish the entire process. The same principle you can apply to additive manufacturing, so that you can able to generate the components. The process distribution, as I told, it is you can have rotation speed and welding speed and plunge force and various tool geometry. So that itself will take care of to create the amount of heat generation for developing the process. So just you can see, just I have modified the tool with a hollow tool instead of solid one used in the friction stir welding. Here I am using friction stir processing for the same machine. The machine is same, only I am changing the design of the tool, that's all. So in the design structure, you can use hollow cylindrical tool. In the hollow cylindrical, just you can insert the filler material into the hollow one. So hollow, the filler material is very, very low melting point temperature material compared to the hollow shoulder. Then you can rotate the shoulder with certain RPM. Due to that, heat is generated. That heat is transferred to the substrate as well as the filler material, so that the material is softens. Then you can give the movement to the shoulder so that the metal is deposited onto the substrate. That is a very simple principle. So additive friction stir deposition is a thermomechanical process. You have a rotation of the shoulder and normal force, filler material, and layer height and transfer speed are the process variables which are used in friction stir additive manufacturing. So these parameters control the heat flow, as I said, and material flow process, which are fully coupled. For the deposited material, the heat generation, dissipation, and transfers mechanisms are similar to the stirred material in friction stir welding or processing. Then relation to friction stir welding and processing, microstructure formation and applicability to non-weldable alloys in both in friction stir welding and processing. A shoulder with a protruding pin is spun at high rate and inserted into the softened material. You can also develop the composite material. That means various materials, aluminum over steel and steel over some other material. You can also develop these components with the multiple materials using this process very easily compared to wire arc or any 3D printing process. Then relation to friction stir welding and processing. In friction stir welding and processing, the stirred material is surrounded and constrained by the material in the form in the thermomechanical. Hello?
Sir. Kumar sir, ఒక్కసారి మళ్ళీ స్టాప్ చేసి మళ్ళీ ఒకసారి షేర్ చేయండి సార్.
Why? What is the problem?
ఏమో సార్, మళ్ళీ ఎవరైనా పార్టిసిపెంట్స్ ప్రెజెంట్ స్క్రీన్ అనేది టైప్ చేసినట్టున్నారు. మళ్ళీ ఒక్కసారి మీరు స్టాప్ మళ్ళీ షేర్ చేయండి సార్.
Okay, fine.
Participants right. Participants don't share the screen. Don't share the screen.
I request all the participants, please don't share your screen, please.
ask them to mute either microphone or the video.
So all of you, please mute your video and mics. Please try to cooperate. Thank you. Sir, మళ్ళీ ఒకసారి మీరు స్క్రీన్ షేర్ చేయండి సార్.
I think I'm not able to share.
Sir, actually what is happening, those who are viewing in the YouTube, they are facing the problem, sir, but for us no problem. Just you 1 second, please share the screen, sir, and you can continue, sir.
నేనేం ఒక్కడే ఎవరో చేస్తున్నారు స్టూడెంట్స్.
Now it is okay, sir. Just you enlarge it, sir. Right, sir. Please continue, sir.
Yeah.
Right.
Yeah. So the relations to friction stir welding and processing, just I am explaining with these two pictures. So this is friction stir welding. This is additive friction deposition. So in friction stir welding, you have a shoulder and the pin. Then this is to be rotated with certain RPM. Because of the rotation, the heat is generated between the rotating shoulder and the non-rotating base plate. Then you can that heat is utilized to softening the material. At that time, you can give the movement to the shoulder in terms of welding speed. Then the material is dragged from the advance into the retreating side and fill the back side of the pin. That is the principle of friction stir welding. So instead of pin, just I am not using the pin, just I am using the hollow shoulder. In the hollow shoulder, I am fixing the filler material, which is going to deposit onto the substrate. And because of the heat generation by the shoulder and the substrate, that heat is utilized to softening this filler material and deposit it onto this. So that is a simple changes in the tool. Then according to deposition rate, you can also give the movement to the shoulder. That mechanism is required in friction stir additive manufacturing process. So this is one video just yesterday I have downloaded friction stir additive manufacturing. So you can also improve the efficiency 30 times the normal production times. So this is the hollow shoulder. In between there is a material which is going to deposit it, that is a filler material. Then according to the deposition rate, you can feed that tool. Okay. Then what are the features and capabilities of this process? The peak temperature of an additive friction stir deposition process normal ranges from 60 to 90% of the melting temperature because of the base of melting and some porosity, hard cracking, elemental segregation, dilution, aggregation, and finally dispersed oxide particle and high residual stresses also come into picture. So that's why you need to optimize the all process parameter to avoid all the problems encountered during the solid state welding process. Yeah, additive friction deposition can use a solid rod made from a caster or wrought alloy as the feed material. The traditional atomized powder feedstock can also be used without stringent requirement on powder attributes, high quality reproducible. Aluminium 6061 and Inconel 625 parts have been manufactured using solid rod feed material, and aluminum molybdenum and aluminum silicon carbide composites have been manufactured from powder. There is no issue because it is a solid state welding process. You can weld, you can deposit any material. So these are the different aluminiums, different magnesium alloys. I'm not going to much details of these. Now I can show you there are two different materials, titanium to aluminum and steel to copper. You can also able to produce these components through friction stir additive manufacturing for various applications. And the scalability, you can also build the large size because there is no much issue at all. And what are the advantages, what are the benefits through friction stir process? One is non-beam and flexible feed material and scalable, no melting, low energy, low cost, and flexible feed material, cast alloys, consolidated powder, high build rate and large scale, ability to repeat, dynamic recrystallization, no stratification, refined grain size, Equates grain size, isotropic property, low porosity. And compared to 3D printing, you can get a lot of advantage in friction stir processing. The limitations, the development of additive friction stir deposition based on technology has focused on increase the part size and build rate. As a result, the shoulder and the filler dimensions are large, leading to large in a plane features. Then next, in additive friction deposition, the deposition path is guided by G-code based hash pattern. Since algorithms are available to automatically convert the CAD file to G-code, it's straightforward to go from a CAD file. Nowadays, the CAD files are available in open literature. You can download the CAD file. That CAD file is converted into G-code. That also available. Then just you can interface the friction stir welding machine according to the CAD file. The tool is going to move. Then buckling is an issue in friction stir additive because you need to add a large amount of force during the processing. That's why the buckling is the main issue for this process. And the tooling also, because there is a lot of wear and tear takes place due to the friction generated. Because of that, you need to develop the various tool materials for improving the wear and tear. Then comparison to other solid state AM processes, the additive friction deposition is a fundamentally different in that it is a material deposition process rather than a sheet lamination process. In addition, the microstructure resulting from the intensive friction stir processing depending on dynamic recovery or dynamic recreation, whereas the gentle ultrasonic process gives a similar microstructure before and after fabrications. Like then coming to the basic idea is what are the additive manufacturing. So what are the advantages of additive manufacturing compared to wire arc and every process has its own advantage. Depending upon our need, we can select a suitable process, then you can able to generate the components. So just I'm giving a light scope on various additive manufacturing technology and what are the steps involved in additive manufacturing technology. So initially you need to generate the CAD file. That CAD file you can convert into STL file. Then STL file is transferred to AM machine. Why we need to convert STL file? But STL file, the machine is only understand the STL file. STL file is a combination of triangles, that is slices, that is converted into total 3D geometry is converted into slices. The slice is the 2 geometry. So each and every slice is a 2 geometry. Then you can add machine parameters, then you can build the components, then you can post process it, then you need to develop the you need to apply this component in various applications. Then why we are so interested in additive manufacturing nowadays? So this is the credit goes to CNC only. So without CNC, there is no AM machines. Without CNC, without CAD, there is no AM machines. So because of the development of CNC and CAD, then we need to generate the AM machines, or we need to produce the AM machines, and we can get the good product, better product, even if it is complex in nature. Suppose if you see the difference between CNC and AM with respect to materials and complexity and accuracy and the geometry, so there are a lot of variations in these two machines. So for example, I need to develop the component with the material as a ceramic material. With the CNC, it is impossible to get the required geometry. Whereas through AM, you can able to generate the component very easily. So AM does not require any irrespective of any materials, but it takes only the energy. At what energy you are supplying, that energy is suitable for melting the required material or not. That is the aim is concerned. So with that, either brittle materials or ductile materials or any other combination of composites, you can able to generate through AM very easily compared to CNC machines. So with respect to complexity, if you want to produce multi-channels for improving the life of the electronic circuits, you can go for complexity channels so that increase the rate of heat transfer. So this is one area people can work. With the complexity of the cooling channels, through conventional CNC machine, it is not possible. Through a machine, it is very easy to produce, even if it is complexity nature, because every layer, it is a small portion of that channel. So that channel is either very in a straight line. But if it is very layer is very, very small, it looks that channel is a straight line. So by building the layers, finally you are going to the complexity of nature of the channel. Then as per the accuracy and the geometry is concerned, that CNC is better than AM process, because accuracy is, we are not getting up to that what we require through AM process, because of so many issues in the CAD file and conversion of CAD to STL file and the machine parameters. So many issues are there. Those issues you can concern to improve the accuracy. This is one area people can work to improve the accuracy of the component through additive manufacturing is one research area. And another area is geometry. Topology optimization we can use to get the final geometry. So with the able to geometry, you can able to that if your geometry is correct, then you can convert that geometry into STL file. Again, you have to lose some features of the object. So if you don't want to lose the features of the object, then you need to apply some optimization, topology optimization techniques, so that you can able to generate the components without using the optimization. Sir, power పోయింది, just hold on. నేను మీకు కనెక్ట్ చేస్తాను. Okay.
Sure, sir. Sure. We will wait.
I request all the participants, please wait for 1 to 2 minutes, sir. Please cooperate.
Is it visible that?
Now it is okay, sir. Your voice is audible.
Okay, fine.
Please continue, sir.
Right.
Yes, sir, it is visible.
Yeah. Stop VLC. Video ఉంటేనే వస్తుంది అది. Okay, window. Yeah. Is it okay?
Slide.
Malay garu.
Sir. Okay, sir. You enlarge it, sir. You enlarge it. Now.
Yeah. So many difficulties.
Due to this COVID, we have led.
Sorry for the interruption because the power is gone in my house. I am connecting through a phone. Now, the difference between CNC and AM, finally, the difference is CNC, we can call it as a 2.5D, whereas AM, we can call it as a 3D. So why it is CNC is called it as a 2.5? So in a one single setup, you cannot generate 3D objects through CNC machining process. At least another setup is required to generate the third dimension in the where the component is fixed in the check. So that's why it is called as a 2.5D process, whereas in AM 3D process. That is the difference. Then you can see this chart, you can save a lot of time through additive manufacturing. This time is you can save from the additive manufacturing process. Then which machine is suitable for your process, so that you can able to see all the charts. So even though I can share these presentations to you, it is very easy to understand. Then you can see the injection molding process and other additive manufacturing process with respect to cost and production volume. So there is some break-even point below, before the break-even point, that is the left side of the break-even point. Injection molding is very costlier than additive manufacturing process, whereas after the breaking point, the injection molding is very low cost compared to additive manufacturing process. So that's why you need to select a process. What is the quantity of production is required for your component? Based on that, you can select a suitable process. So these are the different kinds of applications. I'm not going to details. We are coming to direct energy deposition, where the laser has a power source. That power source is interacting with the powder particles. Then the powder particle is melted and fused onto the substrate. If the the laser is not sufficient, then there is a feedback sensor. That sensor will sense the laser power. If it is not melted, then give the signal to the laser source. Then according to the laser source, power is going to increase, so that you can able to build the components. So direct energy technology, direct DED, DMD, direct metal deposition technology used for generally repair of any structures. So the benefits, speed as in faster product to market. A study performed at the National Center of Manufacturing Science indicates the die production time can reduce by 40% of the DMD technology. So economy, lower tooling costs due to factors including reduction. Then drawbacks, the post-processing involved, the part must be cut from the build substrate, has a rough surface finish and low dimensional accuracy. And die repair and refurbishment applications point, and direct metal prototype, surface modification, aerospace and aircraft components. Then another process, a powder bed fusion process. Here the powder is spread onto the substrate. Then you can apply the laser pore source according to the STL file format. Then according to the STL format, the laser source is going to move. Then the laser power is interact with the powder. The powder is melted and the deposit on the substrate, so that you can be able to finally generate the components. Through additive manufacturing process, the DED and PBD, that is powder bed fusion process, the lot of material is going to waste in this process compared to DED technology. Now, this is another important mechanism involved in either powder bed fusion or DED process. So now here is substrate. Now laser power source is impacting on the substrate. Then some of the laser is reflected back, and some of the laser is scattered, and some of the laser is absorbed by the material, and some of the laser is transmitted. So whatever the laser which is impacting onto the substrate, that laser is, suppose if it is highly absorptivity is more and more. So whatever the energy is supplied to the substrate material, that will be totally absorbed by the material, and melting takes place. Then suppose some material which are having low absorbability like aluminum alloys. So those are highly reflective natures. So whatever the laser which is impinging onto the surface, that will be reflected back. So the absorption of the laser by the material is very less. So in that case, heat content is not sufficient. So that due to that, melting of the material could not be taking place. Now that's why the people can also work in this area using laser as a power source for building the components, highly reflective materials. Just you can coat the material which is having a low reflectivity material to the highly reflective materials. That is enough for the laser processing of the materials. So there are different mechanisms involved. One is solid state sintering, chemical induced binding, and liquid phase sintering, full melting. So in solid state sintering, suppose if you assume 4 particles are combined together, there is a porosity, then you can apply the heat to the 4 particles by the laser interaction. Then due to the laser interaction, the powder particles are going to heat it up and form necking starts. Then finally sintering takes place, then the pore size between the pore particles is very less. Then another mechanism, chemically induced. Because of the presence of SiC, the presence of oxygen, it forms SiO2, binds together a composite SiC and SiO2. So SiO2 is act as a binder to form a composite of SiC and SiO2. So due to the chemical reaction with the presence of oxygen to form SiO2, like zirconium oxide, suppose if it's the aluminum in the presence of nitrogen, aluminum nitride is binds together and form aluminum and aluminum nitrate particles. Then another mechanism is some binding material which are coated or which are added to the powder particles. Because of the energy, laser energy is available, that energy is utilized to melting the binder particles and will be placed between the, will be occupied between the grains so that the bond is formed. Then full melting, this is the normal mechanism, the melting of all the powder particles and allowed to solidify to form this one. So this is one of the mechanism, powder bed fusion. Video is not then drawbacks, applications, medical, aerospace, manufacturing, automotive, and electron beam as another source. So similarly, this is similar to powder bed fusion process as a laser power source. Here instead of laser, electron beam as a source. Because of the electron beam, because of the electron nature of the electron beam, it should be performed under vacuum environment only. So without vacuum, you cannot perform the 3D printing using electron beam as a source, because electron beam is, electrons are very, very small, very low density compared to the oxygen and nitrogen molecules. So that's why you are not getting the accurate penetration, and you cannot be able to generate the heat at a particular place. That's why we need to create a vacuum. But due to the creation of vacuum, the cost of the process very high compared to laser as a power source, and size is also very limited compared to the laser as a power source. So the difference between electron beam and laser beam, electron beam here you can perform under vacuum, whereas this can be performed in inert gas, and mostly conductive materials, it is high absorptive materials. Yeah, what are the benefits? Productivity is increasing, no residual internal stresses, just drawbacks, conductive materials only. Then what is 4D printing? The 4D printing is the process through which a 3D printed object transforms itself into another structure over the influence of external energy input as a temperature, light, or other environments. So this is similar to 3D printing process. After printing, just because of the influence of the external agency, that object dimensions are going to change in the 4th dimension, that is known as 4D printing. There is no confusing at all. We are printing the material, which the material is smart material or functionally accepted material. According to the function, it is going to change the material property dimensions. So however, the 4D printing adds the dimensions of transformation over a time. It is therefore a type of a programmable matter. Just comparison between 3D printing and 4D printing. So here 3D printing metal, and you can be able to static structure. Here you are going to get the dynamic structures because of the influence of the external agency. That dimensions you are going to change. That is, you can call it as a 4D printing. The size changing, just I'm showing the one video. So initially we are printed 3D printed material, then because of the external buoyancy, this is going to change. Yeah. So next to coming to 5D printing, the name of this technology is quite misleading, since 5D printing does not refer to the addition of fifth dimension of the printing. It is not going to add any fifth dimension. So if 5D printing refers to 3D printing using 5-axis 3D printer instead of 3-axis used in conventional 3D printing. 5-axis additive manufacturing essentially builds the object from multiple directions, thus producing stronger parts than regular 3D printing. Yeah, this is another video. Yeah. So some of the research directions you can also see from this. Yeah. So new product development and innovation of the components through additive manufacturing, through wire arc additive manufacturing or hybrid machining process, and biomedical applications. The new materials you are going to develop through friction stage additive manufacturing or 3D printing, and rapid tooling and rapid manufacturing. So geometric modeling, data exchange and software issues, process improvements and development of new process equipments and controls, development of newer applications, aerospace, electronic process modeling and stimulation issues. Then scaling issue, micro to nano level. So with this, I can conclude my lecture. That is open for discussion.
Thank you, sir. Thank you, sir, for your nice presentation, sir. It is very interesting and informative, sir, especially for young research aspirants, those who are interested to do their research in the area of manufacturing, especially additive manufacturing and modification techniques. So thank you, sir. Thank you once again. And now I request all the participants to just ask your questions in the chat box. Then I will inform the speaker to clarify your doubts. So there is one question from Bradley. Which software is used to simulate and design for different types of additive manufacturing?
So normally any CAD file, any CAD software way you can generate the models. Creo software and other softwares are also available. That will convert it into STL file. That STL file is transferred to the machine.
Excuse me, sir.
Sir.
Please. This is Professor Kirango from Karigudi, Tamil Nadu. Sir, regarding this 3D printing and 5D printing, the strength of the material product for 3D printing and 5D printing, is there any difference of its strength?
5D printing is stronger than 3D printing components.
How can we say, sir?
Because you can change the direction where you are going to print the other dimensions of the components. Earlier I have shown one video. So if you don't have any access with a 3D printing, some overhanging structures, that is overhanging. Due to overhanging nature, due to that there is a change in the properties. That's why we can reduce the properties compared to 5D printing process.
The engineering applications, is any product is necessary for getting the different strength properties?
So normally ductility is the main criteria for any engineering applications.
Yes, sir.
For all EM products, normally you can come across low ductile materials compared to conventional manufacturing process because of the rapid solidification. So if you manage the rapid solidification issues, or if you manage the heat management issues, you can able to generate the near net shape components, and also you can reduce the porosity. Thereby you can increase the ductility of the entire components.
It may be the different applications.
Yeah.
Thank you so much. Yes, sir.
Thank you, sir. Thank you.
One more question from UG student, sir. He want to pursue his career in rapid prototyping, specifically in automotive industry. He's asking that what is the scope of rapid prototyping in automotive industries?
So not only automotive industries, aerospace industries also people are using. The GE, General Electrical Motors, they are producing all the components through metal additive manufacturing process nowadays.
And sir, one more question from Mr. Ram Mohan Reddy. He's asking like, which metal 3D printer replaces CNC?
Yeah, just I have shown one of the slide is CNC versus AM. In that, suppose all the materials you can perform through in AM process, whereas in CNC it is not. For example, ceramic materials, if you want to do CNC programming or CNC machines, so it is very difficult to get geometry. I'm not looking for just machining of the ceramic material, but geometry perspective point of view, AM is a suitable process.
Right, sir. Thank you, sir. One more query, sir, from Akshay Chaudhary. What are the defects in 3D printing? How can we increase the aesthetic properties of printed objects?
So main problem is the porosity is one issue. One is a big issue. So to control the parameters, to control the heat management during solidification of the printed components, we can able to reduce the porosity. That is one. Then another issue is any oxides which are formed during the printing process of metals. Those oxides you can eliminate by maintaining the particular temperature. At what temperature you are not going to get the oxides. Suppose if you want to add new material to the previous material, it is very difficult to get good properties in fusion metal additive.
At the end of the second section, we will be covering the
Sir, one more participant, Sumit Rai, sir, is asking like, how is buckling affecting friction stir additive manufacturing and what are its effects?
Please repeat again.
Sir, the one query from Sumit Rai. He is asking like, how is buckling affecting friction stir additive manufacturing and what are its effects? Buckling effects.
So we cannot avoid. That's why the size, height of the component is restricted in friction stir additive manufacturing, because we need vertical force definitely. Without vertical force, we cannot generate the heat. So that's why there is a limitation in friction stir additive manufacturing.
Sir, one more question, sir. Pradeep Chan, sir, is asking a benchmark problem for a simulating additive manufacturing problem.
Yeah, benchmark. Okay. You can take any problem which are published in the journals. Then you can apply this additive manufacturing. Then you can compare the properties. Suppose if you are getting the good properties through your process, then you need to publish a paper with the good mechanical properties. I think so.
One more query from
in our country, where 5D printing technology used.
Right.
So I think GE people are using 5D printing technology.
So now I request all the participants, please send your queries in a mail. Anyway, we will provide the email of the speaker, Dr. Kumar sir, in the WhatsApp group. Please share your queries in mail. So thank you, Kumar sir. Once again, thank you, sir. Thank you very much for your sparing your valuable time. Thank you, sir.
So thank you very much, sir. I can leave the meeting.
Sir, thank you, sir.
Shall I leave the meeting?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you.
Sir, Kumar sir, this is Satish. Sir, on my behalf, thank you very much, sir.
Yeah, thank you, sir. Thank you.
Now I request Mr. Amarnath, co-coordinator of this today's webinar, to introduce our today's second speaker, Dr. M.V. Satish Kumar. Amarnath.
Sir, good afternoon, everyone. Today's second speaker is Dr. M.V. Satish Kumar, sir. He has done his graduation in mechanical engineering from Regional Engineering College, REC Warangal, MTech in Computer Integrated Manufacturing from REC Warangal. Sir has done his PhD in mechanical engineering from JNTU Hyderabad. Sir is presently working as professor and head of Mechanical Engineering Department, Kamla Institute of Technology and Science, Singapore, Hyderabad. Sir has got 26 years of teaching experience, and in area of interest includes flexible manufacturing systems, operation management, and evolutionary algorithms. Sir has published 45 research papers at various preferred national and international journals. Sir is a reviewer for International Journal of Advanced Manufacturing Technology and International Journal of Production Research. Now I request Dr. M.V. Satish Kumar sir to share his knowledge by presentation. Thank you, sir. Sir.
Good morning, everyone. Sorry, good afternoon, everyone. Thank you, Mr. Amar, for your nice introduction. And before I start my lecture, I would like to thank my earlier speaker, Dr. A. Kumar Garu, on my own behalf and also on behalf of Mechanical Engineering Department. As head of the department, I would like to thank him for sparing his valuable time for giving this wonderful talk. And before I start my lecture, I would like to mention that Kumar sir has completed his talk with wonderful videos and colorful images, but whereas mine is mostly a theoretical part, the participant has to excuse me. And also I would like to say that the main intention of my lecture is to give an overview of optimization algorithms, because of course there might be many learned people in this group, but my main intention is youngsters and students to whom I want to give a bit of information which I know. Rather than knowledge, I can say just I want to share the information what I know regarding evolutionary algorithms, which is part of optimization algorithms, and also swarm intelligence, so that they can pursue further and they can use these optimization techniques or tools or algorithms in their research. These tools, the beauty of these algorithms is they can use in any type of manufacturing or even any type of optimization problem. They can use these algorithms for optimization of that is in scheduling or in thermal area, in manufacturing area, in any area. They can use these algorithms. That is the beauty of this. So they are using many other tools, but they can also consider this tool or this algorithm for optimizing their problem. So I will start. My presentation goes like this. First, I will talk about what is optimization and what are the goals of optimization, and then one or two small problems of optimization. Then why we need to go for algorithms that we will speak. Then among the different algorithms, I will take up a few algorithms because time constraint is there. So we will take up only few algorithms, 2 from evolutionary algorithms, that is genetic algorithms and differential evolution, and 2 more from swarm intelligence, that is particle swarm optimization and ant colony algorithm. So these 4, the 2 in brief, I want to cover. So if you have any queries, you can mail me. I'm always ready to help you in whatever way I want, I can. So with this, I would like to start my presentation. So coming to today's topic, because the algorithms we are talking about are meant for optimization. So let us see what is optimization. As all of you know, optimization can be defined as the technique of finding the values of the process variables which yields the best results for a particular performance criterion under consideration. So the performance criterion we are deciding, and also the values are they are process variables. So of course it is everywhere in our day-to-day life, not only in industries, not only in research. This optimization is everywhere in our day-to-day life. Knowingly or unknowingly, we are solving these optimization problems. For example, we will go to the college, institute from home, or we will come back to the home. Automatically, we will try for the shortest path. Similarly, if you want to do some personal work, we will prioritize and we will optimize the time so that all the works which are prioritized according to the priority, we will complete in time. Similarly, budgeting at home or budgeting at any institution or organization. So these things are simple examples which I want to share for optimization in our day-to-day life also. Similarly, this is a mathematical problem everybody knows. So traveling salesman problem. That is a person who starts from a city and n number of cities he has to cover, and he has to come back to the original city, and what is the shortest path, in how much time he can cover. That is the problem. So it is a well-known mathematical problem. If you take 20 cities are there, a person has to cover 20 cities and he has to come back to the original city. There are many possibilities. You can see on the screen 20 factorial ways. So you have to search all those ways. What is the best way? So such problems are really tough to solve. So by normal methods, optimization techniques, So we may use some advanced methods or advanced tools or algorithms, I can say, for solving such problems. Another problem is a knapsack problem. Of course, just for fun, I am saying a thief enters a house and he wants to pick up the things. Then he will not carry that is heavy weights like a TV and a refrigerator, but instead he will concentrate on a diamond ring or gold or something, which is knapsack problem is nothing but given a set of items with different values and weights, then what is the combination of components with the minimum weight and maximum value? So the thief naturally looks for minimum weight because he has to carry and maximum value. He will not concentrate on refrigerator or TV, but rather he will concentrate on a diamond ring or some other lightweight items with more value. So these are all, this is also, of course, this is also an optimization problem. Then normally, what is the goal of optimization? So here, to find the values of the variables that minimize or maximize the objective function. For every optimization problem, there will be an objective function, and our aim is either to minimize or maximize. This depends on the type of problem. For some problems, we will try to minimize, and for some few more problems, we will try to maximize. So the goal of optimization in industrial scenario is to select the best solution among the large number of alternatives. Because just now we have seen traveling salesman problem. So a number of alternative solutions are possible, but our concern is what is the best among the all. If not best, that is, if not the optimum, at least we want to go for near optimum. So that is our goal. So, and unfortunately, no single method or algorithm of optimization exists that can be applied efficiently to all problems, because problem to problem, it varies. The complexity may vary and the variables may vary. So you cannot say that this is the algorithm which can solve any type of optimization problem. There is no such algorithm. So the user has to decide. He has to test with the different algorithms, and then he has to decide what is the better algorithm for a particular problem. So any optimization problem, so it will depend primarily on the character of the objective function, whether it is known explicitly or not. So that is one factor, and also nature of the constraints. We will see what are constraints. So nature of constraints, we must have an idea, and number of independent and dependent variables. Also, we must have an idea before we solve an optimization problem. So constraints, so a set of constraints that allow unknowns to take on certain values but exclude others. For simple example, I want to say in scheduling problem, precedence constraint is one example. So we will consider precedence constraints in scheduling. What is precedence constraint? That means unless the preceding operation is completed, we cannot go for the succeeding operation. That is, unless drilling operation is completed, we cannot go for boring or reaming. So when we are scheduling, we have to keep that precedence constraints into mind. So similarly for other problems, different types of constraints will be there. And most of the problems, almost all the problems, they will have objective function. So that is either it may be maximization or it may be minimization, but almost every problem will have objective function. But there are rare possibilities with no objective function. But in reality, we can say that that is in some cases, for example, design of integrated circuit layouts. This is an example. So the goal is to find a set of variables that satisfy the constraints of the model. Here, the user does not particularly want to optimize anything. Here, whether constraints are satisfied or not, that is our intention, but we are not interested in maximizing or minimizing anything. So such functions, sometimes we will come across, which are called no objective function. Okay, this type of problems is usually called a feasibility problem. And as I told you, variables and constraints both will be there in an optimization problem. But among these two, variables are essential. If there are no variables, we cannot define the objective function of the problem, and also constraints. But constraints are not essential. In fact, the field of unconstrained optimization is a large and important one for which a lot of algorithms and softwares are available. And it's been argued that almost all problems really do have constraints, even though we say sometimes constraints will not be there. But in reality, we can say that most of the problems, they will have constraints. And models. So modeling is the process of identifying objective function, variables, and constraints. So the goal of model is to get insight of the problem. So if we want to get an insight into the problem, we need to model the problem. So a good mathematical model of the problem is needed for effective optimization. And algorithms, even though models are available, most of the models for real world problems are too complicated to solve with a paper and pen. So an effective and reliable numerical algorithm is needed to solve such problems. So modeling is there, but they have their own limitations. So that is how the necessity of algorithms coming into picture. So there is no universal optimization algorithm, as I told you earlier. So even though a variety of optimization algorithms are available in literature, but we cannot say that this is the algorithm, one algorithm which can solve any type of optimization problem. But it may be any optimization algorithm, we will expect certain characteristics from that. What are those characteristics? What we expect is robustness. That is good performance for a wide class of problems. At least it may not be better, it may not be the best for any problem, but at least for a wide class of problems, it should be giving good performance. Similarly, efficiency should be there, that is computer time, because we are using computers for running the code. So computer time is also another component we have to consider. And similarly, accuracy of the algorithm, where we are landing finally. So these three normally we expect from any optimization algorithm. How the process goes, given a design problem, for example, optimization. So then we will realize the need for optimization. Then once we realize the need, then we will choose the variables in the problem. And once the variables are chosen, we will also identify the constraints. What are the constraints in the problem to be solved? Then we will set up variable bounds, that is boundaries will be fixed. Then we will choose a particular optimization algorithm. We will select according to the problem, and then finally we will obtain the solution. This is how normally a procedure takes place. Then of course, most of you know, there are a variety of optimization algorithms. They can be broadly classified into two things. One is deterministic algorithms and the other is probabilistic algorithms. What is the difference? So these algorithms, coming to deterministic algorithms, these algorithms follow a specific rule and searches the solution space by moving from one solution to the other. So please try to understand here, they are moving one by one solution by the other, and also they are following a specific rule. They are following the specific rule and moving one place to another, but only in the solution space, but one solution at a time. That is deterministic algorithm. Then what is probabilistic? So these algorithms are stochastic in nature and with probabilistic transition rules. They will search the entire space randomly. Okay, so with some probability. So this is the basic difference between these two algorithms. And what are the examples for different algorithms? In deterministic algorithms, of course, we have covered few. There may be few more algorithms under deterministic category which are missing here. Just to give you an idea, the difference between deterministic and probabilistic, I have shown this slide. So state space search, branch and bound, algebraic geometry, these comes under deterministic algorithms. Whereas probabilistic, a lot of algorithms are available under this category, like hill climbing, random optimization, simulated annealing, tabu search, and so on. Similarly, you can see the classification here. We are concentrating today on soft computing. That is, soft computing is the area under which evolutionary algorithms comes and also swarm intelligence comes. So in today's lecture, we are not concentrating on other algorithms, even though there are a variety of algorithms like Monte Carlo algorithm or other algorithms. And under soft computing, again, you can see on the screen very clearly, evolutionary computation is there. So evolutionary algorithms indirectly, they comes under evolutionary computation actually. So evolutionary computation algorithms, again, there are a variety of evolutionary algorithms like genetic algorithms, learning classifier systems, evolutionary programming, evolution strategies, and of course, genetic programming. And even sometimes we can say in the literature, few people say that differential evolution is again a separate one which comes under evolutionary algorithms. Then all these evolutionary algorithms, especially genetic algorithms, they will mimic the human beings. Anyhow, we will go in detail. Just I want to tell, they will mimic the human beings. That is, two parents will produce the children, and automatically the genes of the parents will appear in the children also. Based on that, some characteristics we may see, maybe black hair or gray hair in some cases, blue eyes or black eyes in some cases. So these are all because of genes from the parents. So based on that, this algorithm was developed. Similarly, differential evolution also comes under evolutionary algorithms, which is it is a sort of modification to the genetic algorithms, but where we will use vectors. So these two I would like to touch upon. I would like to give an overview. Of course, the participants can get in-depth knowledge later and they can apply to their problems, but just I want to stress upon these are the tools which you can also think about for your optimization problems. Similarly, under swarm intelligence, again there are so many algorithms under swarm intelligence. I will show you the slide which gives the different types of swarm intelligence algorithms. But in this presentation, I would like to limit myself to particle swarm optimization and ant colony optimization, these two. So in total, we are going to give, I will try to give an overview of 4 algorithms, 2 under evolutionary algorithms, genetic algorithms, and differential evolution, and 2 more under swarm intelligence, that is particle swarm optimization and ant colony optimization. So first, most of the traditional, why, even though these deterministic and probabilistic are available, why we are talking about evolutionary? What is their need? Let us discuss briefly. Most of the traditional optimization algorithms which are based on gradient methods, and they have the possibility of getting trapped in local minimum, that is local optimum, depending on their degree of non-linearity and initial guess. So unfortunately, none of the traditional algorithms guarantee the global optimum. So this is one point where we are thinking about other algorithms, other alternative algorithms. So similarly, in the challenges are there. Suppose some of the problems, most of the optimization problems are not trivial and they are NP hard. So these challenges are there. So similarly, feature selection is another problem in most of the optimization problem. If you have a 32 feature problem, then so many number of possibilities, combinations are there. So searching one solution, one particular best solution is a tough task. So these are there are some limitations with the deterministic algorithms. That is how. So this side slows again. So even though it is looking like a minimum, but it is local minimum. But it is not. Sorry, it is maximum, but it is not a local maximum, but it is not a global maximum. So our target is to search for global optimum, global maximum, or global minimum. In this case, in this graph, it is maximum. So global maximum we want, but not local maximum. So there are some certain issues with traditional algorithms. So how to solve? So the way the literature has given us is, that is, we can divide and conquer. That means solution search space can be divided and conquered. That is, you divide the search space and then search parallelly the search space. That is the best method people have found. So the solution for this is parallel search. So conducting searching in different areas simultaneously. Rather than moving one by one, you will go simultaneously at different places, you will search. That is parallel searching. That too population based. That means at a time, we will take a group of solutions, and this is called population based. Similarly, we will in parallel search, we will try to avoid unfortunate starting positions and also employ heuristic methods to effectively explore the space. So here, that is exploration of the space is also important. Exploitation is one important factor. Exploration is one important factor. Exploitation is covering the total search space, okay, for optimal searching for optimal solutions. Whereas exploring at a one space, you don't want to leave any stone unturned. So that is exploration. So with this concept, the evolutionary algorithms came into picture. So now let us see what are evolutionary algorithms. So it is nothing but, I told, learning from nature, I told you. So you can see, of course, how we are now flying by planes, because we have seen the humankind has got motivated by looking at the birds, and that is how now today we are flying by aeroplanes or even rockets, anything. The idea of flying came by nature only, from nature only. The human beings imitated the nature. So this is one simplest example. Now, even the algorithms also got inspired from nature only. That is how all the algorithms, that is especially evolutionary algorithms or nature-inspired algorithms, have been developed by different eminent people. So coming to evolutionary algorithms, evolution as proposed by Charles Darwin is a process in nature which individuals adapt to their environment by preserving the features that makes the individual compete, and the others, that is eliminating the others which make them weaker. So here, if a species has to stay back on the earth, means it has to compete. So in the process, it has to, some features are there which make the species, dinosaurs are not there now on the earth. So some species, they have vanished. So just an example I am quoting. So unless if you want to, that means stay back, survival of the fittest is the rule, that is Charles Darwin's rule. So here, you have to, if you want to compete, you have to preserve the best qualities in you, and you have to eliminate the weak qualities in you. So that is what we have to learn from the nature. So evolutionary algorithms, exactly what they will do is same. They will simulate the nature. The same evolutionary algorithms, they will simulate the procedure, evolutionary procedure on a computer. So evolutionary algorithms have proved themselves as a better alternative for many optimization problems like scheduling. Scheduling is one example which I have quoted, but it can be applied for many problems, a variety of problems. So what is the working principle of EA? So create a sample of ES, that is create a sample of random solutions to a problem. That is, initially I told you already, it is a population based. So we will create an initial population, okay, then evaluate the fitness of each solution. Here, every problem, every solution of the problem will have a fitness. That is, in general, on the earth, nature will evaluate the fitness of individual. Whereas here in the evolutionary algorithms, so we have to have some fitness function. Then we will determine the solutions to be used to create the next generation. That is, I told you in the case of genetic algorithms, parents will produce offsprings. Our offsprings are nothing but children. Then among the different solutions available in a search space, then we will choose few solutions as parents. So that is very, very important. So determine the solutions to be used, selection we will call. So once this is done, we will go for the next solution. Of course, there are some operations, genetic operators are performed on these two. We will describe in the next slide. Then that is how we will create the new solution. So from a group of solutions, we are picking few solutions as parents. We are performing some operations, and that is evolutionary operators. We are applying on those solutions, parents. Then we are getting the next generation, that is children. Then we will repeat this process until a termination criteria is achieved. For example, this area, whatever I told you, the cycle, this is called a generation. That is selection of parents, then selection of initial population, creation of initial population, selection of parents, applying two operators like a crossover and mutation, and getting the children. This completes from parents to children, this completes one generation. So in a computer, we will give the termination criteria like the process should be repeated for 10 generations, 100 generations, 15 generations. Like that, we will have termination criteria. So the evolutionary procedure will be repeated till the termination criterion is satisfied. So what we need to solve an optimization problem through EA? So we need to have proper representation of the potential solution. This is very important. Similarly, correct way to create an initial population of the potential solution. This is also to be correctly done. And also an evaluation function should be there. I told you just now to calculate the fitness of the individual. So these are important, and also selection procedure must be chosen properly. So unless you choose the parents properly, then the children, you cannot expect better. So if better parents are chosen, you can expect better children or even best children normally. So sometimes there is a possibility, sometimes irrespective of the parents also, sometimes there is a possibility, but we will, because we have the choice in our hand, so we will try to choose the best parents. Similarly, evolutionary operators like crossover and mutation to alter the composition of the children. And similarly, parameters like population size, number of generations, probability of crossover and mutation, these are to be selected appropriately. Then advantages of EA. So when compared to the traditional methods, evolutionary algorithms have the advantage that they need only little problem specific knowledge, and hence they can be applied to a broad range of problems. And ES can be applied to complex problems with discontinuous, non-differentiable, and even other problems also. So their response to external process parameters is robust when compared to the previous methods, and hence does not need fine-tuning of these operators, even for applying them to different problems. So evolutionary algorithms use probabilistic transition rules, as I told earlier, but not deterministic, because they comes under probabilistic algorithms, not deterministic. And evolutionary algorithms are generally more straightforward to apply because no restrictions for the definition of the objective function exist. And as a variety of evolutionary algorithms are available, problem-specific EA can be chosen by the end user because a variety of algorithms are available. And evolutionary algorithms can provide a number of potential solutions to a given problem, and the final choice is left to the user. It can give a number of solutions among, of course, better solutions only. You can choose one among them. That is also possible, especially in multi-objectives. You will get Pareto optimal solutions. You can choose one among them. So ES, that is evolutionary algorithms, search a population of points in parallel, but not just a single point at a time. And ES do not require derivative information or other auxiliary knowledge. Only the objective function and corresponding fitness levels influence the direction search. So coming to the evolutionary algorithms, in the earlier slide, I have shown a variety of evolutionary algorithms are there, but we will restrict only for few: genetic algorithms and differential evolution. Even though evolution strategies, genetic programming, evolutionary programming, all these comes under evolutionary algorithms. Coming to genetic algorithms, so they are good at mapping from the natural process of evolution onto a computer system. So as I mentioned just now, this is purely, it is imitating the nature, parents, are used to produce children. So binary coding is normally used. And coming, of course, I will come across GS in detail, but just I want to give few points about evolution strategies also, which also comes under evolutionary algorithms. So evolutionary strategies are different when compared to GA, mainly in the selection process. In GA, next generation is created from the parental population, choosing individuals, maybe depending on their fitness. Whereas in ES, a temporary population is created. It has different size than parental population. This is where the two differs. And in this step, fitness values are not important. Individuals in the temporary population undergo crossover and mutation, whereas in genetic algorithms, it is not the case. So from such populations, an assumed number of best individuals are selected to next generation. That is how ES proceeds. And ES operates on vectors of the floating point numbers, whereas classical GA operates on binary vectors. Coming to genetic programming, another part of evolutionary algorithms, another member of evolutionary algorithms, which is relatively new, and it is a specialized form of GA which operates on very specific type of solutions using modified genetic operators. So actually it was developed by COSA as an attempt to find the way for automatic generation of the program codes when the evaluation criteria for their proper operation is known. Of course, genetic operators are specialized working on trees. This is the basic difference. In case of genetic programming, we are using trees. Crossover as exchanging the subtrees, mutation as change of node or leaf. And because the search solution is a program, the evolved potential solutions are coded in the form of trees instead of linear chromosomes. Similarly, and GP differs, that is genetic programming differs from GA, the used coding schema, but the loop is same. But only thing is here we will use trees. And coming to evolutionary programming, it was developed as a tool for discovering the grammar of the unknown language. But however, evolutionary program became more popular when it was proposed as the numerical optimization technique. And EP is also similar to ES, evolutionary strategies, but with one essential difference. In evolutionary programming, the new population of individuals is created by mutating every individual from the parental solution. Just now discussed, in case of ES, it was not like that. A temporary population was created. And whereas in ES, every individual has the same probability to be selected to the temporary population, but here it is not so in case of evolutionary programming. And in case of evolutionary programming, the mutation is based on random perturbation of the values of the particular genes. And the newly created and parental populations are the same size. Finally, new generation of the population is created using ranking selection. Of course, different types of selection operators are there. This is one type of selection. And coming to differential evolution, the last member in the evolutionary algorithms, anyhow, we are going to discuss in detail about this. It is a type of evolutionary algorithms useful mainly for the function of optimization in continuous search spaces. Principal version of the DA, of course, it has principal version is developed by Storm and Price, but later on different versions were developed by others. And the main advantages of DE when compared to GA, I can say it is a modified version of GA, but still it has advantages over GA, like it is easy to use, it has efficient memory utilization, lower computational complexity, lower computational effort, that is faster convergence, and DE algorithm prevents the solution of sticking at a local optimum. So these are some advantages. And let us see some more, let us lay some more light on genetic algorithms, so that I told you in the beginning, my focus is just to give an information to the youngsters so that they can pursue further, they can use this wonderful tool, all these tools, wonderful tools for their respective areas. So coming to the genetic algorithms, so they are random evolutionary search algorithms which mimics the principles of natural genetics. It was developed long back in 1975 by John Halland, and it is a set of procedures which, when repeated, enables the solutions to the specific problem. And before looking at the steps, let us see some terms involved in genetic algorithm. So objective, of course, irrespective of the algorithm, objective is the function to be considered for minimization or maximization. It need not be only for GA. For any algorithm, it will be there. But it's coming to gene. This is a single feature within a chromosome or a working subunit of DNA. Because we will talk about gene in terms of genetic. That is how genetic algorithms are named. And similarly, gene triad. That is, color of eyes is a triad. Color of hair is a triad. Similarly, apple is other possible. Allele is another possible. Color of eyes need not be only gray. It can blue. It can be black also, or it need not be blue. It can be like that. Similarly, genotype. The actual genes carried by an individual, whereas phenotype, the physical characteristics into which genes are translated. So this is just some awareness about the terminology I'm trying to give. And similarly, chromosome is nothing but set of genes, which gives the genetic description of individual. So in our optimization problems, chromosome is nothing but a solution. So which consists of genes. Genes are variables. So fitness. So this is a measure of how well a parameter set performs. So this may vary from problem to problem. So similarly, population is another term which we have to have an idea. So the number of chromosomes, they form a population, single population. And it can be any number. Population size, it may be 10, 20, 100, something like that. So population size is number of chromosomes considered, whereas generation is one complete cycle. Earlier I told you the process of selecting, that is initial population, then selecting the parents, applying operators, and getting the next generation. This completes one cycle. This is called generation. And of course, I want to introduce few more terms like selection. Selection, it is the mechanism by which parents are chosen for producing offspring. Offspring is nothing but children. In our normal language, we will call children, but here we will say offspring, to be passed on to the next generation. So selection tends to pick best population elements as parents, because we will assume that the best parent will produce the best offspring. So crossover, what it will do? So it is an operator used for reproduction. It takes parent pairs, that is a pair of parents will produce children. So that is what crossover will do. It is an operator in evolutionary algorithm. So just you can see on the screen, so parent A and parent B are crossover operation taking place, and you can see the first, there is a dividing line you can see. So 101 from parent A, if you look at the children, 101 of children is same as parent. But if you observe the second part of the children, it is not 100, but it is 10101. You can observe first half before the partition line. The partition line is from parent A. Second half from after partition line is from parent B. That is how child 1 is produced. Similarly, child 2. You can observe on the screen. If you keenly observe, 101, 100, 101 is parent. That is the two parents. Then children you can observe before partition line. That is how single point crossover we will say. Of course, a variety of crossovers are there. A variety of crossover points are there. You can see here, this is how it is shown. So 101, and you can see children 101. But next part, you can see this is the next part. That is first part of this, second part of this. You can see here, first part is 101, second part is this. Both first part from A and second part from B has produced child 1. Similarly, first part from this children, second part from this parent, and second part from this parent. So it is from child 2, child 1 and child 2. Of course, in the downside, I have shown 2-point crossover. So like that, you can have different types of crossovers. Then mutation. Mutation is another operator. It is an operator which exchanges gene with another gene within the chromosome. And of course, it is slightly varies. You can see one is replaced with 0. Similarly, of course, the same thing I have shown, but I want to say just steps involved: initialization, random selection, that is evaluation of fitness. Once initial population is generated, its evaluation fitness will be evaluated, then parents will be selected, then reproduction, that is crossover and mutation will be done, and that is normally steps involved. The same, of course, just I want to show the same thing in a flowchart form. So this is how it takes place. So just to give an idea, a small example I have taken. So this is a population. You can see here initial population, and their fitness is shown on the right side. So similarly, we will choose among this population. We will choose. So you please observe this. Here fitness of fifth member is more, whereas fitness of the last member is less. So that is normally what we will. There are different ways for again selection. So roulette wheel selection is one type of selection, which is based on it is probable selection, but based on the fitness value, the probability. The more fitter parent, more probability for selection. So that is based on that is the formula is shown here. So now you can see here fifth parent is repeated. You can see that is fifth parent with more fitness is repeated, whereas sixth, which is weaker one, is not selected in the next generation. So we have done now crossover. You can see this is the crossover on the same generation population. We have selected two parents, S1 and S2, and we have performed crossover. And of course, we have performed mutation also. And if you observe, the fitness has changed slightly. Of course, it is only one generation. So like that, we can go on by generation to generation. We can increase the fitness, and also we can get the better solution. And coming to differential evolution, the second member in evolutionary algorithms. So it is also a population-based algorithm, and it is an improved version of genetic algorithms, I can say. And it is here vectors are used. It is NP vectors are used, each of dimension d, where d is the variables in the optimization problem. And of course, it is also randomly searching the space. So here, I want to introduce the main concept of DE here. Now, basically, two vectors are randomly chosen from the population. Suppose different vectors are available. Each vector is nothing but a solution. So different vectors from the available vectors, two vectors are randomly chosen, randomly selected from the population, and their vector difference will be calculated. And you can see here, this is how I have shown XR2G minus XR3G. So this is the difference. So this difference is multiplied by a weighing factor F. So once it is fixed at the beginning of the algorithm, normally it will be maintained throughout the algorithm. So that F we will be fixing, and we will choose another algorithm. So this step is known as differential variation, and the result is known as the mutant vector. So what you can see on the left side, this is mutant vector, and difference of two vectors we have taken, we have multiplied with a scaling factor, which we have added to the third vector. So this the resulting vector is known as mutant vector. So you can see here. So the same concept you can see here. So here this is XR1, okay, and this is second vector, this is third vector. The difference of those two vectors is added to the this vector. So this is how you are arriving at a new vector. So difference of two vectors is multiplied by a scaling factor, which is added to the third vector. You got mutant vector, but this is not end of the algorithm. So getting for how do you get mutant vector is shown here. So once mutant vector is known, then a target vector is also selected from the population, and the target vector and mutant vector now they are subjected to crossover. So this shows crossover. Of course, for all dimensions in the vector, we will do this operation, crossover operation, and then based on that, we will generate a random number. So we have the crossover probability we have already fixed. So based on whether this random number is less than or equal to this CR or not, we will choose either this or this. If this is satisfied, we will choose this, which is nothing but mutant vector. Otherwise, this is target vector. So we will get these two, then we will have crossover operation is performed in differential evolution. So if the trial vector and target vector are compared, so now first we got mutant vector, then we have got trial vector after crossover. Now target vector is with us. Now we will compare trial vector and target vector, and whichever is fittest, that we will take it for next generation. So these trial vector and target vector are compared to decide the member for the next generation. So this is how the process continues: random generation of initial population, then evaluation of population, new population. The same, very similar to previous, that is genetic algorithms method. But here we will mutation is very, very important in case of differential evolution, whereas crossover is more important in genetic algorithms. So you can see here a small example. So there is a problem which has 6 individuals, and the number of dimensions are 5. So here this is the target vector I have chosen, and these two are randomly chosen. I told you just now R2, XR2 and XR3. So these two randomly chosen vectors are there. So the difference of these two, so here it is 0.86. Okay, so the difference is multiplied. Here in the table I have shown you F is 0.8. F is 0.8. So if you calculate the difference and if you multiply it, then you will get the weight, this factor, F into difference, F into XR2 minus XR3 you will get. Then you will get mutant vector. Once mutant vector is obtained, then you have chosen this as target vector. Target vector and mutant vector are crossover is taking place here. Then again crossover trial vector you are getting. The trial vector and again target vector are compared. So every dimension by dimension, we will compare target vector and trial vector. And then here, for example, this is from target vector. Okay. So similarly, comparison of GA and DE, of course, it has advantages over DE has many advantages over GA. So it is mainly crossover in case of GA, but mutation in case of DE, I told you. So this is, of course, genetic algorithms. All parents are replaced by their offsprings, irrespective of their fitness at the end of every generation. But if this process of probability, good parent strings being replaced with its deteriorated child, this possibility is there in case of GA. But in case of DA, this possibility is eliminated because every child, even it has to compete with parents to get its place in the next generation. And of course, the Preisenstein, the people who have developed this have given one basic strategy, but later other strategies were also developed. So coming to this basic strategy, so it is generally denoted by DE by X by Y by Z. So DE is nothing but differential evolution. X represents either it is a randomly chosen vector or best vector. The next slide will give you more clarity. And Y is the number of differences. Difference of 2 vectors we are taking are different of one set of vectors or 2 sets of vectors we are taking. Similarly, Z stands for crossover, whether it is exponential or not. So based on that, we will see. So similarly, D is number of dimensions in the problem. So similarly, of course, see other important variables, other important parameters are CR value. We have to be very careful in selecting. Similarly, these are the different strategies I told you. So here, DE stands for differential evolution. This is one type of strategy. Best means in a population, best vector will be chosen first. Then one is only difference of one set of vectors is chosen, and exponential crossover. Similarly, if you take two sets, this is instead of 2, there are 4 vectors. Similarly, random to best may be there. Here it is taken best in the population, randomly chosen, R stands for random. So like that. So these are all important things in case of evolution, differential evolution, population size, scaling factor, CR value, all these things are important. And coming to swarm intelligence. So the next part of my presentation is swarm intelligence. So already I told you evolutionary algorithms, they are imitating the nature. Very similar to that, these algorithms are also developed, but they are imitating the swarm. Rather than human beings, they are imitating animals and other things. So of course, you know this, a single neuron in the human brain can respond only to what neurons connected to it are doing. But all of them, if all the neurons are connected, it can be bright brain, a brilliant brain like Albert Einstein. So similarly, an individual ant is not a very bright, but ants in a colony, so as a group, they can do remarkable things. This is how inspired swarm intelligence algorithms got inspiration from the nature. So it is again learning from nature only. So we know in day-to-day life, birds are flocking, ants are moving, but to see how we can use their intelligence for the optimization. So out of these two, particle swarm optimization and nautical optimization, we are concentrating here, even though there are many. So coming to particle swarm optimization, what here is here we are saying particle is nothing but a solution. So this is based on that is birds when they are flying. You can see here on the screen, birds when they are flying, they have two things. One is their own experience and the other is the social experience. That is neighboring birds will also share information. So that is based on this only this algorithm was developed. So birds flocking is one of the best example. So bird when they are in search of food, so they determine its velocity not only based on their personal experience but also through the information gained through interaction with other members of the flock. So this is how, that is their experience is one part and others' experience is another part. So this the people have incorporated into algorithm. That is how PSO was developed. So PSO algorithm is not only a tool for optimization, but also a tool for representing socio-cognition of human and artificial agents based on principles of social psychology. So a PSO system combines local search methods with global search methods. So we are balancing exploration and exploitation. So what we are expecting, what properties we are expecting for a particles? Particle is, we can say a bird is a particle or a particle is a solution in our case. So ability to exchange information with its neighbors. We are expecting this property, and ability to memorize a previous position, and also ability to use information to make decision. So there are three things. They are getting information, they are exchanging information from neighbors, they are memorizing where from they have started, now where they landing. So which is the best? They can decide. Ability to use information to make a decision. These properties we are that is expecting for a particle to use in PSO. So in particle swarm technology, each particle is a potential solution to the available solutions, and this group we are calling it as swarm. A particle swarm we are calling. So every particle has position and also velocity. So position vector of a particle with respect to the origin of search space represents a trial solution only. Okay. Then the basic steps involved in PSO are, first step is we will initialize a population of particles with position and velocity. Every particle will have position and also velocity on d dimensions of the problem. So next step is we will update the velocity. That is, each particle velocity we will update, for which we will use the formula shown in figure. So here, this is velocity at the next instance. If v of t is instance t, but this indicates the next instance, velocity of a particular particle at the next instance, if you want to know. So this is the formula given by the people who have developed it. So here VID is the velocity of particle, then PID is the particle's best previous. You can see here best previous position. Just now I told you it has the ability to memorize. So what is its present position? What is its previous position? What is the best among them? So it can memorize. So this is PID. So the PID stands for best, P best, that is local best we can say. Similarly, particles position, XID is particles position at teeth interval. So XID stands for, that is whereas it is it is representing the position, whereas it is representing the velocity. And the other factors which are shown are W is inertia weight, which is here, W is inertia weight, and whereas these two are the constants, psi1 and psi2 stands for uniformly distributed random numbers, and whereas this C1 and C2 are self-confidence and swarm confidence. Because here you can see GID is another term. So GID is the best position among all the particles in the swarm. Just now I have given one more property is it can exchange the information. So what is its present position? What is its best position till now? Similarly, what is the best position among all others? In a group, different particles are getting different P bests, that is its local bests, but among them, which is the global best? So it will memorize. So this algorithm will use all these parameters in calculating the velocity in the next instance. Once velocity is known, we can find out the position in the next instance. So the acceleration constants C1 and C2 are very important here, and there's adjustment of these particle constants is also very, very important, and normally it will vary between 0.1 to 1. And here large inertia weight is also important, and large inertia weight if you have, then it will lead to searching new areas. If you reduce the value of omega, that is inertia weight, it will fine tuning the search. So that's why normally people suggest, that is it will at the beginning maximum number of iterations if you take, and if it is current iteration, then as the number of iterations increases, first we will go for more search, that is exploration will take place, exploitation will take place, then fine tuning exploration will take place. So once velocity is known, then we can find out position in the next state. That is, this is position in the next instant, position in the previous instant. If velocity is added to that, then we can find out the position in the next instance. So next, once this process is over, so map the position of each particle into a solution space and evaluate its fitness. As basically all these algorithms are based on fitness evaluation. So we got a swarm of first generation, we got a swarm of second generation, and of course we are evaluating the fitness. So then loop until the process is repeated required number of times. So initialize the particles, evaluate the fitness, compare and update at every stage fitness value with the P best and G best. This is its own experience. This is global, that is among the swarm. So once these steps are completed, then whether stopping criteria, that is, as I told you earlier, generation, number of generations, for example, 100 generations we kept as stopping criteria. If 100 generations are over, we will, that means close, and whatever best among them we got, we will say it as best solution. Unless it is not satisfied, we will repeat. So again, update the velocity and position. If the stopping criterion is not met, just repeat the procedure. So this is how we will go for. Then, of course, it has advantages and disadvantages, easy to perform, few parameters to adjust, and efficient in global search. Whereas slow convergence in refined search stage, weak local search ability, these are the disadvantages. And another point is, of course, this particle swarm optimization can also be hybridized with other algorithms. For example, people have hybridized with the genetic algorithms because mutation which is available in genetic algorithms can be combined here in PSO. So that is how we will say hybrid algorithm, a combination of genetic algorithms and PSO. Similarly, there are a variety of applications of PSO in all areas. That is, need not be in mechanical. Even other areas also we can apply. And coming to the last part of my presentation, the last algorithm of my presentation, ant colony algorithm. So just let us see the screen. So ants day to day in life, we might not have observed ants keenly, but they are moving from the nest to the place where their food is there. So when they are moving, they are optimizing the problem. They are choosing a shortest path. So they are using their intelligence to that means search the shortest path. Even though a number of ways, in a zigzag way also, the ants can move from the nest to the food. But after some time, you can see all ants are moving in a particular path only. That is the shortest path. How it is possible? Let us see. Let us say in the initial stage, 2 ants have started from nest, but they have chosen 2 randomly different paths. But you can observe on the screen, the first path are on the right side ant, it has already reached the food, whereas the left side ant, it has not yet reached the food because the path is longer than the previous one. That is, right side ant has chosen unknowingly the right side ant has chosen a shorter path. So what happens is, once the food has chosen, it wants to store it again in the nest. So again, the first ant is second ant is moving, but first ant is also returning back to its nest. So in the process, so actually what is happening here is, when the ants are moving, they will lay the pheromone. So you can see here a chemical by name pheromone. So they will lay on the path in which they are moving. So a chemical they will lay on the path. So here, because of this, the first path was longer one, second path was shorter one. But ants, what they will do is, they don't have any intelligence except that they will choose the path on whichever path pheromone is more. If the thicker pheromone is there, if there are 2 paths available for ants, they will choose a path on which pheromone is thicker and thicker. They will not choose a path on which pheromone level is lighter. So that is what they will do. They will just simply follow this rule. That's all. Because in this case, the first path, the first ant has already reached and coming back. So pheromone level has been increased in this path. Whereas this was reached late, so still it is only lighter. Whereas first ant has already started returning back. So pheromone on this path is more. So automatically the second ant also follows the same path. So this is what it is happening. Then the second, the ant again repeats, but naturally, automatically, this is the path left over. And another characteristic of pheromone is, as time passes, it evaporates. The pheromone evaporates. It stands only for, it remains only for some time. But after some time, if no ant is following that path, automatically it evaporates in nature. So here, the second path, again, ants are moving. That's why it is getting strengthened, whereas the first path on which no ant is moving, it is getting evaporated. So after some time, then automatically all the, you can see, so far, this is the best path. This is the best path. But a third ant randomly chosen, again, one more path. Now you can see this is the path. You can imagine now, automatically, this will be the shortest path. After some time, this will be pheromone on this path will be stronger and stronger. Even this will also get evaporated, and all ants will start moving from nest to the food, only following this path, which is the shortest path and on which more and more pheromone is there. Similarly, when they are moving an obstacle also, they will follow the same rule, because an obstacle is there on their way. If they move on this way, it is shortest path. If they move on this way, it is the longest path. The same principle they will apply here. That is same pheromone. So that's why automatically after some time, you can see all the ants are following shortest path. So they are just simply following the pheromone strength, and automatically they are following the shortest path. So this is the nature from which people got inspired and they have started implementing this in the algorithms for finding out optimum solutions. So natural ants, they will choose shortest path, I have discussed just now. And route selection, of course, ants are forced to decide whether they should go left or right. And the choice that is made is a random decision. Of course, I told you, first ant also chosen randomly, second ant also chosen randomly, but ultimately third ant, which has chosen the shortest path, it also randomly chosen the path. But pheromone accumulation is faster on the shortest path or shorter path, and the difference in pheromone content between the two paths over time makes the ants to choose the shorter path. And different optimization problems have been explored using a simulation of this real ant behavior. So, of course, this is same. Let us see. This is the real ant, but of course, real ants, they don't have memory allocation. They don't know how to evaluate the quality of solution. They don't know the knowledge of distance estimation. But we will incorporate, just like we have incorporated in particle swarm, memory and memorizing the p-best and g-best. Similarly, we are incorporating few characteristics in the natural ant. Then we are getting an artificial ant. So these with these natural ant pheromone and similarly memory allocation, quality of solution, distance, we will that means we will find artificial ant. So these can be used for many problems, like traveling salesman problem is the best problem, a well-known problem, of course, NP hard. And you can see place each ant in randomly in a chosen city. So once they are moving, you just that means use the same concept as pheromone here. So for any ant k, probability of moving from state I to state j depends on the combination of two values. One is attractiveness and trial level. So attractiveness indicates in the previous that is a formula. Attractiveness indicates the desirability of that move, whereas trial level indicates how proficient it has been in the past. So this is the formula used in case of ant colony algorithm. So quantity of pheromone deposited and heuristic distance. Okay, and of course here the importance of the trial intensity in the probabilistic transition is alpha, and the importance of the attractiveness of the trial segment is beta. And this is how it will pheromone update. Already I have shown the formula. So this is another example in our problem in our engineering. We can say if you want to use a robotic arm to drill a number of bits, just like traveling salesman problem. So a number of drills are to be number of holes are to be drilled, where to start and to come back to the original state, and what is the best way. This is also application of TSP only for manufacturing, we can say. So these are a few different algorithms. I think I have given some idea about different algorithms like genetic algorithms, particles and differential evolution, particles optimization, and anti-colony optimization. My request again is my only intention in this lecture is youngsters can learn more and more about these algorithms, and they can use these algorithms for their optimization problems in maybe in whatever area they are. So only that is my intention of this, nothing else. But just I want to share 1, 2 or 3 slides. Just people are doing a lot of that is what are the advancements in this area. Genetic algorithms, it was started in 1975, but you can see on the screen till 2018 work is going on. That means they have modified the genetic algorithm. If you see micro GA was developed by so and so person, Krishna Kumar, in 1989. Similarly, this is non-dominated sorting algorithm. Similarly, some algorithms for multi-objective. Similarly, hierarchical cellular, dynamic rule-based, fluid GA, block-based GA. Like that, different developments have come into picture, and different people have contributed for developing GA for different purposes. So what they have done is given here. Who is the person contributed is given here, and in chronological order, how GAs have been that means what are the different advancements in GA, starting from genetic algorithms in 1975 to block-based GA in 2018. Maybe some more may be missing. Whatever I could get from literature have been shown here. Similarly, genetic programming also, since 1992 onwards, 2018, different people have contributed and they have changed the basic, they have developed for a few modifications they have. So this is how they have developed. Similarly, differential evolution, even though it was started by Stone and Price in 1997, still till 2018 only data I have collected. Now after that I don't have. So maybe SADE, DE is multi-populational DE is there. So different memory-based DE is there. So different people have developed. Similarly, evolutionary strategies were also developed like this from 1973 to till date 2018, not till date 2018, different years have been developed. Similarly, evolutionary programming also from 1966 to 2018. So you can see different things there. And coming to swarm intelligence, similar, I have given picture about only few like particle swarm and ant colony. Just for the sake of benefit of participants, you can pursue many of these algorithms. Ant colony, particle swarm are two which I have covered, but bee system is there, bacterial foraging is there, beehive is there, bacterial colony is there, bee colony is there, virtual bees are there, cat swarm is there. So firefly algorithm, bat algorithm. So like that, there are so many. So even this list continues. So even wolf search is there, social spider optimization is there, artificial wolf is there, crow search is there, dynamic virtual bats algorithm is there. Of course, just to give an awareness, I too don't have any idea about these algorithms, but there are, if you want to use these algorithms for your optimization problems, just I want to tell you, these are the possibilities. And similarly, people have published papers, that too in Web of Sciences. In Web of Sciences, these are the publications from 2000 to 2018. These are the number of publications category wise, evolutionary strategies, evolutionary programming, and put together. Similarly, this slide indicates swarm intelligence. SI stands for swarm intelligence, PSO, and ant colony. People are contributing that means, and they are producing wonderful papers and Web of Sciences and IEEE export, and this is the source. Similarly, people are using for different areas also. They are not only confined to mechanical area. People from electrical engineering, electronics engineering, civil engineering, computer science, from different areas, people have published papers on GA, GP, that is genetic programming, DE, ES, EP, all put together. So many papers are published in from 2000 to 2018. Similarly, in GA also, a variety of authors have published number of papers. So just I would like to conclude here. Once again, I thank all the participants for your patient learning. And again, repeatedly, I am saying the main intention of this lecture is give an awareness to this. That means participants. There are a variety of algorithms which are in the literature. If you want, you can use them for different types of problems. So this is what I want to say. Thank you. Thank you, one and all.
Thank you, sir, for your nice presentation. Sir, you have covered various types of evolutionary algorithms elaboratedly, and the participants, those who are doing the research and those who wanted to use this type of algorithms, I hope they have got some information and enhanced their knowledge in the areas of various types of optimization algorithms. Thank you, sir. Thank you once again. So I request all the participants, please send your queries to mail ID, speaker mail ID, because already the time is 1:30, the lunch time. So you can send your queries to mail ID of our speaker, second speaker. Then we will provide the email ID of the speaker in the WhatsApp group. And before concluding my side, I want to present vote of thanks on behalf of Department of Mechanical Engineering, KIT Singapore, and the organizing team. I thank the management and principal sir for permitting us to conduct today's one-day webinar on advances in manufacturing processes and optimization algorithms. And my sincere thanks to today's two speakers. Number one is Dr. A. Kumar sir, as well as number two is Dr. M. Satish Kumar sir, for sparing their valuable time and presenting their lectures elaborately. And also thank our department faculty members and technical team, those who supported for organizing this webinar and making this program grand success. And lastly, I thank all the participants for attending this webinar and patiently listening for today's webinar. Thank you, sir. Thank you, one and all. So we will provide the feedback link in WhatsApp group, and please fill the feedback link, and immediately the certificate is generated. So thank you, sir. Thank you, one and all. Thank you. The session is